Hi, in this video, I will introduce an ongoing work during my PhD regarding a novel hybrid method for solving combinatorial problems. For the purpose of scaling, we consider to use incomplete search to weakly find high-quality solutions, especially for large-scale instances in industrial problems. Local search is an example. We also envisage to boost the performance with conflict learning during the search. In this work, we focus on solving constraint satisfaction problems. To illustrate our approach, we consider problems which can be decomposed into two levels of decisions. At the master level, we have a set of constraints CM, which are selection or allocation constraints, and it should be easy to find an assignment that satisfies these constraints. On the other hand, we have a more complicated constraints such as sequencing at the slave level. These constraints depend on the decision made at the master level and certainly are much harder to solve compared to problems at the master level. In general, the slave subproblem is still a hard combinatorial problem. Let's take some concrete examples. The first example is the Orienteering problem with time windows, which is a variant of vehicle routing problem. In this problem, we have a set of n clients, each given with a reward Ri, a service time, and also a time window. These time window constraints make the problem harder because we need to visit the client during each available time window. So the main objective is, in a limited time, select a subset of clients to visit and maximize the total collected rewards. Let's denote a Boolean variable xi is equal to 1 if the client ci is selected. Then we can decompose this problem into two subproblems. At the master level, we care about the selection of clients to visit, so that the total collected reward must be greater than a defined lower bound. The constraint routable at the slave level means that we need to find a feasible tour to visit selected clients within the allowed time windows. We remark that constraints in CS are actually an instance of traveling salesman problem with time windows. Let's take another example with the case of flexible job shop scheduling. So we have a set of n jobs to process on m machines. Each job consists of a sequence of operations, and each operation OI has a list of mi alternative machines. It means this operation can be processed on one of these alternative machines. The objective is thus to find a schedule to process on operations and minimize the maxspan, which is the total completion time. Similarly, we denote xi is equal to v if operation OI is processed on the machine v. Then Cm are constraints on the selection of machine for each operation. And with the selection as Cm, the constraints of CS are about the scheduling of operation on selected machines given an upper bound on the maxspan. And CS now is an instance of job shop scheduling problem. So our proposed approach is mainly summarized within the schema we will show here. As you can see, we have two modules that interact during the search to progressively find the solution of the CSP. Precisely, the master module incrementally makes decisions on which client are selected or on which machine the operation is processed, and then send them to the slave module to modify the subproblem. The slave module uses a local search solver to weakly check if we can find a feasible solution. If so, the master continues its job. Otherwise, it is expected to return an explanation of the failure, and then the master will memorize it for the future search. So the conflict learned during the search at the slave level have the solver not to check again and again the visited region or inconsistent ones. These explanations are potentially invalid, though they are also added to the master problem for diversifying research. One of the main parts of this approach is how to explain the failure. In fact, a conflict is a set of decisions made at the master level that can explain the failure occurred at the slave level. Obviously, the short conflicts will be more interesting since we can print larger parts of such space. So the core principle is, given the current decision A and the subproblem B now is unknown, remark that it's not unsolved because we are dealing with the incomplete search. So in order to find the explanation, we focus on finding decisions that can lead to a change in the subproblem consistencies. Precisely, if we assign a variable is I in A and the slave subproblem becomes sad, it means is I should be included in the set of conflicts. Formally, the final explanation AC is in the form of a clause like this. AC is equal to a big O of not is I is equal to VI. Then we expect to store on the conflicts in a long-term memory at the master level. Obviously, the biggest challenge here is the risk of memory explosion. To handle this problem, we propose to use compact data structures such as decision diagrams like OPTW or MDD to memorize or learn conflicts. Additionally, such representations allow to execute some basic query in polytime, such as verifying if an assignment violates learn conflicts, instruct selection that respect all the constraints, or also add new conflicts. Several experiments have been carried out for both the orienteering problem and the flexible job sort scheduling. In the case of the orienteering problem, since we deal with only Boolean variables, we use OPTW to store on conflicts. We also chose the method of iOS as the baseline since our solver is mainly based on the iOS solver. The main difference is that we make use of an OPTW in our solver to manage conflicts. Many of the best-known solutions have been recovered by our approach. The computational time is also very competitive. The number of nodes in OPTW is far less than the number of filed conflicts. This shows the efficiency of the use of OPTW. Considering the problem of flexible job sort, we use the MDD to store conflicts. However, our current solver has been able to reach the best known regarding the mesh band compared to other solvers. Several reasons are our local search solver at the slave level as well as the performance of explain function remain ineffective. To summarize, we are working on a hybrid method for solving the combinatorial problem as a sequence of CSP. We are also dealing with incomplete search and knowledge base. So the experimental result showed that we need to do many improvements in the future. Some potential directions are to intensify the search or to speed up and improve the learning phase. Besides, the optimization of the knowledge base is also important, especially when the number of conflicts increases. And last but not least, another perspective is to handle the uncertainty where some information could be dynamically changed. In such case, the knowledge base, thanks to its genericity, would be reused to perform the search in slave problems. And this is also the end of the presentation. Thank you for your attention.